Hey, welcome back, everybody. So now we want to talk about a line integral of the second type, which computes work. So specifically, we want to compute the work it takes to push a particle along a curve through a vector field. So let's dive right in. So let's suppose we have the following situation. So let's say we want to evaluate f dot dr, where the vector field or the force field is given by the following. So let's say we've got f of x, y, z is equal to, let's say we've got x plus y squared. Let's say we've got x, z, and then y plus z. And let's say the path or the curve c is given by some vector function. Let's say r of t is equal to t squared, comma t cubed, comma minus 2t. And let's say our parameter t goes from 0 to 2. So the first thing we want to do is make sense of this and write it in a computable form. So what's sort of the right way to think about this? So the line integral over c of f dot dr. Well, what do we really mean by f dot dr? It's the force field or the vector field dot dr. But to make this computable, we want to introduce some parameter t. So we're going to integrate from a to b based on our parameter, right, from a to b. And then we want to take our vector field and evaluate it along the curve. And essentially, by doing this, we're just restricting how much of the vector field we consider. We're only interested with the vector field that's along our curve or path. So this will be f of x of t, y of t, z of t, dot, well, dr, we're going to think about that as dr dt, dt. Okay, so what do we mean by x of t, y of t, z of t? Those are given by the vector function, right? This is the function that's describing the curve. And again, by evaluating our vector field at x of t, y of t, z of t, we only consider how much of the vector field is acting on the curve. Okay, so just to make this clear, this is what we mean by x of t. This is y of t, and this is z of t. Okay, so what about our bounds? Well, again, our bounds correspond to the parameter. So we're going to be integrating from 0 to 2. And then we want to evaluate our vector field at t squared, comma t cubed, comma minus 2t. And then we want to dot this with dr dt, which we'll compute in just a moment. All right, so this doesn't seem so bad. So again, how do I make sense of this? I'm going to go to my vector field, and everywhere I see an x, so I'm going to plug in x squared. Everywhere I see a y, I'm going to plug in, I'm sorry, did I say x squared? Everywhere I see an x, I'm going to plug in t squared. Everywhere I see a y, I'm going to plug in t cubed. And everywhere I see a z, I'm going to plug in minus 2t. Okay. All right, so just evaluating the vector field here gives us the following. So we need x plus y squared, right? So x plus y squared. So if I take this and square it, that's t to the 6. So that's x plus y squared. So that goes here. So now we need x times z. Well, x times z. So x times z gives us the following. So that's minus 2t cubed. And then lastly, we need y plus z. Well, y plus z gives us the following. So that's t cubed minus 2t. So that's exactly y plus z. Okay, so that's our vector field evaluated at x of t, y of t, z of t. So now we need dr dt. That's exactly the derivative of this. And do remember that is a dot product there. And so that looks like it's going to be 2t, 3t squared, minus 2. So there's your derivative, and remember all this dt. Okay, so what do we need? Well, it looks like we need our bounds, right? Of course we need our bounds. So now we want to compute the dot product carefully. So now we compute the dot product. So remember the dot product of two vector functions should be some scalar function. So computing the dot product, let's see here. So we want this times this. So that's going to be, let's see here. So 2t times t squared plus t to the 6. So that seems fine. And now we want this times this, right? Computing the dot product. So that's going to be minus 2t cubed times 3t squared. And then this times this. So that'll be plus minus 2 times the quantity t cubed minus 2t. So minus 2 times 2 cubed minus 2t. And all of that is dt. Of course, we're going to double check. So this times this is here. This times this is here. And this times this is exactly here. Okay, that seems fine. So we've computed the dot product. Now we want to just carry through with our algebra. Let's see what we get here. All right, so by the distributive property, it looks like we've got 2t cubed plus 2t to the 7th, right? And so here we've got minus 6t to the 5th. And here it looks like minus 2t cubed plus 4t. All right, so there's our algebra. And now let's see, do we have any like terms? It looks like the cubes are like terms, right? Those are actually gonna, hey, it looks like they're gonna cancel. How about that? So those are gone. So that's pretty nice. So we've got 2t to the 7th minus 6t to the 5th plus 4t dt. So we've now reduced this to a Calc 1 style integral. So that seems pretty nice. Okay, so now we're just going to integrate in the usual way using our power rule. So what do we have here? So this looks like 2t to the 8th over 8. So that's t to the 8th over 4. And what else do we have here? So this is going to be, well, that's just going to be t to the 6 when we integrate here. And that should be 2t squared. Evaluating from 0 to 2. Well, this will completely vanish at 0, so I only need to evaluate this at 2. So this will give me 2 to the 8th over 4 minus 2 to the 6 plus 2 times 2 squared. But we notice something, because 2 to the 8th over 4, that's the same thing as 2 to the 8th over 2 squared. But that's exactly 2 to the 6. So those will cancel. So these will actually cancel, and that gives me 8. And that's the value of my line integral.